Hey gang, welcome back to the old physics dungeon here. Um, I'm going to start teaching you about sound today. And so I'm going to start out by telling you this truth, which is that if you were a whale right now, you would hear a tone because of the shaking of my hand. And I can't shake it fast enough for you to hear it as a tone, as a human. But whales have a lower end of the frequency that they can pick up and sense as a tone, as sound, of 5 hertz. So anything shaking through the air at 5 hertz or more will sound like a tone or a pitch to a whale. Humans have a range that goes from about 20 hertz to 20,000 hertz. Those are kind of rough numbers. If you are older, like someone in their 60s or 70s perhaps, might not be able to hear anywhere near 20,000 hertz anymore. As you get older, the higher end of your frequency range tends to become less and less, to the point where as a 70 or 80-year-old you may only be able to hear up to about 12 or 13,000 hertz. And against the air more than 5 times a second or so, and so it did not produce for you an audible tone. You can check. There are lots of free apps that you can use to play around with what the highest limit of your frequency range for hearing is. I'd suggest doing that if you're interested. But what I can do is I can get this stick to shake the air more than 5 times a second, and up to about 20 times a second, so that it becomes audible to you as a tone. So I'm going to try to do that now. Hopefully my phone's microphone can pick this up, and you're hearing this is a very low rumbly tone. Also, you might have noticed that the stick spins, and it spins and tilts itself upward and then downward over and over again. And you can notice that halfway through its time spinning tilted upward, it's going fastest, and the same thing for downward. I will loosely say that it tilts up and down because of the Bernoulli effect, but I don't really want to get into that here. So, you just saw that sound is produced when the air gets smacked or pushed several times a second. For humans to hear it, it's got to be at least 20 times a second, and not more than 20,000 or so. And really, for me anymore, I can hear up to about 16 to 17,000 hertz, but I cannot hear any frequencies higher than that. You all being younger, and maybe you've tried it with that app, might be close to 20,000. Okay, so I don't get to do this in person, which is really disappointing, but I've got several ways to prove to you all that when you hit a tuning fork, and this one is labeled, if you can see it, it's labeled 320, which is an E. That means that these forks swing back and forward 320 times a second, and it's hard to see. I can hit it and make it vibrate. Maybe it looks kind of fuzzy on the camera, but you definitely couldn't count the oscillations or anything like that. And so I've had students say, it doesn't look like it's moving. So to them, I proved it in a couple different ways. One of them, I would have gladly tricked Gabe into volunteering for, and it goes like this. I told him that sound, or would have told Gabe that sound has a smell to it. And so I'd strike it and then put it right up to his nose and get a reaction out of him. And he would definitely agree at that point that these forks are moving. The other one, I would have gladly fooled, let's say Nick. maybe I could have tricked Nick into this other one, which is that if you look really close, sound can produce light when you put it through water. That's the premise. And so I would hit the tuning fork, and I would get Nick to put his face up real close to this, and then of course soak him. So there's a couple of pieces of evidence. There's another one coming. Here's another piece of evidence that all that sound really is a shaking of the air as far as we usually experience it. I've got this toothpick that's attached to the tuning fork, and I have smoked this side of this microscope film, microscope slide here. So what I'm going to do is I'm going to hit the tuning fork and make it vibrate as we claim it's doing, and then drag it across this, and we should be able to see that there was some shaking of the air that was going on in the first place, and that the tuning forks are actually just wiggling back and forth. Here goes. Well, I can see it really well. I'm hoping that the camera can pick it up, but there it is. I just dragged it from over here to over there. The next thing that I have for you is not something that I own anymore. Used to have one. It's called a Siren Disk, and it is the way that, at least somewhere around maybe 100 years ago, the original sirens for emergency vehicles were produced. It's basically, the one that I had was a metal plate, but the one on the YouTube video I found, that's a really antique one, is made of wood. And so mine was just this metal disc that had holes punched through it, and they were regularly spaced holes, and that's important because if they're not regularly spaced, you end up with white noise. But mine were regularly spaced around in circles, and this disc, which as you can see had 48 holes punched in it on the outer ring, it would be rotated with a mechanical rotator in order to produce sound. What you would do is you would blow through a straw through the holes, and so the air would pass through the disc as puffs of air. The counter that was on it would count the number of revolutions of the disc. Each revolution represented 48 puffs of air, so every time it would go around once, the air that was being pushed through the openings would be chopped up 48 times. It would occur in blasts or pulses 48 times for every revolution. The timer, a person with a stopwatch, would record the time that it spent spinning around. And for example, we may have counted with the counter 223 revolutions, which is the same thing as 10,704 puffs of air, because 223 times 48 per revolution would give us that many puffs of air in a time of whatever the stopwatch said, which may have been 12.07 seconds. If that was the case, then the frequency produced would be 886.8 puffs per second. This is a frequency of 86.8 hertz. Now, what we'd try and do then is match that frequency to the best of our ability with any of our tuning forks. And I did not have tuning forks that were that high a frequency. I did have something like this one, which is an A. This one says 426.7. A, I think concert A might be 426.7. I'm not a music person, at least not officially, so maybe that's A5 on a piano, but I'm not really sure. Here's C, which is 512, and I want to say that the B that's between those is somewhere around 480. Either way, it's nowhere near 886.8 puffs per second or hertz. So it doesn't match any of my tuning forks. Oh, here it is. I guess I should have read. It's very close to, on a piano, A5, which was 880 hertz. which is exactly double the frequency of an A4, which is 440, which would closely match the tone that's produced by the Siren Disk in that case. And if you'd like to hear what one of these things sounds like when it's running, check out the YouTube video that's in the add-on to your notebook. This next segment is something that you should try to do at your house if you have the materials, which are not very complicated or difficult to find. All you'll need is 2 pieces of string and a metal coat hanger. Here's mine. Got a metal coat hanger, and here's one piece of string that's attached to one end, and the other piece of string is attached to the other end. And those pieces of string are wrapped around my fingers. And the purpose of this is to show you and to have you experience the way that sound conducts really, really well through a solid and not as well through liquids, and definitely nowhere near as well through gases. Most of the sound that you experience is traveling to your ears through gases, through the air. So it doesn't really sound the way that it could, and all the frequencies that are produced definitely don't show up or don't have as much energy when they make it to your ears when the sound travels through the air. So I'm going to do what you should do, which is to hang this coat hanger from my 2 fingers in the strings, and if I hit it against a table, it doesn't sound like anything. You can't even hear it on the video, I'm sure. I'll be quiet to make sure though. But if you hold your fingers in your ears while you do that, you'll get the full spectrum of all the sounds that are produced, all the frequencies, when you hit this against the table with your fingers in your ears. So I'm going to turn the camera and try and do that, and then make a face so that you know exactly how amazing it was. Ready? You should try it yourself. Here's another way that I can show you that a solid will conduct sound much better than gases do. Here's a music box. This music box is wound up and is playing a really old song called School Days. And what you can do is you can touch this solid surface to another solid surface with a much bigger area, and you can set up standing waves on that surface. In this case, this whiteboard. So you know what it sounds like when it's not attached to it, and hopefully this comes across in the video, but it sounds quite different when you attach it to the solid. Here is another example of how sound waves really are just vibrations of the air that are picked up by larger objects to be amplified. This is called a Talkie Tape. There's a link to another YouTube video where somebody with a different message is explaining how this might work. And I'm not sure that you can see the little ridges on this piece of plastic, but they're there. Mine happens to be attached to this speaker. This is a cup. And when I drag my fingernail, my thumbnail, across those ridges, the vibrations are picked up by this entire surface, and it amplifies the sound that we hear. We hear it as a phrase. Maybe you can detect what it's saying. This one, in case you didn't pick up on it, says, and it's the truth, it says, "Science is fun." Now I'm going to show you how a record player can work. This is a really simple design. They're microscopic, but the grooves in the record are just like the Talkie Tape that you just saw. It's filled with little bumps, little craters, and mountains on a microscopic level. And all that we're going to do here is we're going to hold this needle still. This is just a pin. and we're going to let it sit in those grooves, and then we're going to rotate the record around so that the needle bumps up and down on those grooves in the record. And when it bumps up and down, it shakes this entire piece of cardboard, which is going to act as the speaker. So here goes. Okay, now that we're establishing how it is that we can produce sound, I would like to offer some proof about what type of wave sound is. And maybe based on what you've seen so far, particularly the tuning fork example for producing sound, maybe you have an idea about what type of wave it is. In either case, we would have to choose between whether it's likely to be a transverse or a compression wave. The behavior that some waves partake in that others don't, that we could use to distinguish which type of wave it is, at this point in what we know is going to be polarization. We do know that transverse waves vibrate up and down, I would say, if they're traveling from left to right. In other words, the vibration is perpendicular to the direction that the energy is traveling in. So, transverse waves can be polarized and compression waves cannot. So, what I have here, this is really scientific stuff, big budget stuff. What I have here is a polarizer. This is a slit that sound waves can travel through. And if sound is a transverse wave, then the sound that is making its way to the phone right now would have to be polarized. It is only vibrating vertically if it's a transverse wave. Here's another polarizer, and now the sound that you're getting is side-to-side sound if it's a transverse wave. And what should be possible if sound is a transverse wave is that I should be able to cross the polarizers, and when I cross the polarizers, you might not be able to hear, but I was talking the entire time. No? Okay. Sound is a compression wave. Sound is a compression wave because, again, like the tuning fork might have you imagine, the spoke of the tuning fork hits the air, pushes it forward, compresses it, and creates a high pressure zone right in front of it, and then shakes backward and lowers the pressure in front of it by kind of stretching the air out. And it does that hundreds of times every second. It shakes the air or compresses it, and then creates these high and low pressure zones. This often, in this case, 426.7 times a second. At this point, you're definitely going to want to pause and try your very best to understand the animation that is referred to about the motion of individual particles in compression waves. There's a website, a web link that has been shared with you. It is in your extension to your notebook, and you might have to stare at it for 15 minutes and then ask questions about it to understand it. But that is a topic and a type of question that the IB loves to ask, so you need to be prepared for it. We established before that there is a wave equation that is V equals lambda f. The speed that the wave travels through the medium is equal to its wavelength times its frequency. This still applies for sound and actually can help us quite a bit in our understanding of what sound waves might look like. We should be able to picture them after we do a little calculation here. So here goes. V equals lambda f, and for an A, which is slightly different from this tuning fork A that I have, we might have a frequency of 440 hertz. The speed of sound, as you found out earlier in your sophomore year, is about 340 meters per second. in these temperatures, which is about 1100 feet per second. V equals lambda f then gives us that the wavelength of this A note, this sound, which is again close to this sound, is 2.5 feet. That 2.5 foot wavelength represents the entire length of this sound wave as it travels through the air. So when I just struck that tuning fork, I was creating centers of compression surrounding centers of rarefaction, which you remember might mean stretched out or lower pressure air, that were 2.5 feet long. So about like, well, I guess like from my hand over here to like my hand, maybe 2.5 of these. This is about a foot wide. Also, you should picture that there is every 2.5 feet, there's a high pressure zone, a low pressure zone, and a high pressure zone, and that repeats. And everywhere that can hear that sound, if you are anywhere that can hear that sound, it means that between you and that tuning fork, or you and any tone you experience at all in your life, the air, if that's the medium you're listening to it through, is compressed and stretched every 2.5 feet for that tone through the entire medium, through any of the material stuff that you can hear that tone through. Now we're ready to start to get into some of the other wave behaviors that we've already talked about with mechanical waves and water waves. So first, we will admit that sound waves do reflect, and the reflections have a special name. They are called echoes. These echoes or reflections of sound can be focused or spread out, like you saw happen with water waves. There are two really good examples that, again, I've shared links for you to look into on your own. But if you've ever seen a person with this clear plastic dish running along the sidelines in a professional or college football game, you've seen someone using the focusing of sound waves. That's called a parabolic microphone, and it uses the focusing of sound waves to capture in-game action during live broadcasts of football games. The other one is common in museums. I know I've been to one in the Museum of Science and Industry in Chicago. It's a whisper room. So check the links in your add-on to your notebook and do some exploring. Our next wave behavior for sound is to talk about refraction of sound. Refraction, you'll recall, is when sound waves, or waves in general, change their speed based on a change in their medium. In air, temperature changes cause changes in speed, which results in refraction of sound waves. So there are two really good examples of this. The first of which is called a temperature inversion over a lake. It's not common, overnight at least, but sometimes we end up with conditions over lakes where there is cool air below warm air. The cool air is where sounds travel more slowly than in the warm air. This is the slow zone and the fast zone. And so you'll remember from refraction before, just like when a car has one of its tires in the mud and others on pavement, or when soldiers walk through Russian mud, or when lifeguards, soon to be out of jobs, calculate the best path to go from sand through water to save a person. The same effect impacts the travel of sound, or how loud things seem to be. So here is a person asking a friend right next to them, "How are you?" And here is somebody else that maybe you know saying, "Thanks for asking." And the way that this works is this person who's all the way across a lake, maybe hundreds of yards away, can hear this person as clearly as if they were right next to them, because those temperature zones for the air result in the sounds that traveled outward away from this person, that traveled outward and upward, speeding up on the left side, we could say, with our particle model for refraction. And so the sounds that would have received or reached this person from all the way across the lake still do, but now some of the sound that was sent up and away from that person who was speaking at normal volume on the one side of the lake, some of those sounds change their direction because they have refracted, because they travel faster up here than they do down there. And so they change direction. These sound waves change direction and are able to reach all the way across to the other shore, making it seem to this person like that person was right next to them. Our next example of the refraction of sound waves that you might have experienced is called heat lightning. And if you haven't heard of heat lightning, it is lightning that is seen but not heard. And the conditions that cause it to happen that way, for this person to be able to see it but not hear it, are that there's a layer of warm air just above the ground, and above that, high above that, there is cooler air. This warm air acts as a fast medium for sound waves to travel through, and the cool air is a slower one. So this person who is ready to hear the sound from the lightning strike doesn't end up hearing it at all, because those sound waves speed up as they pass through the fast medium and slow down as they pass through this cool, slow medium of air. And so whatever sound waves would have normally reached this person instead pass right over their head. So they could still see the lightning strike, but they can't hear it at all. This typically happens in the summertime when we get a thunderstorm, and there's a lot of warm air near the surface of the earth, but cooler air up above. We don't even hear the thunder, we just see the lightning. In your water waves video, we talked about something called absorption. I also mentioned it with mechanical waves. But absorption is related to the fact that long wavelength waves travel farther than short wavelength waves do, because the long wavelength waves lose less energy over the same distance than short wavelength waves do. With our mechanical waves, we gave an example that basically blamed friction for this fact, the fact that high frequency waves don't travel as far. There are many good examples with sound of this. Here are a couple. If you hear the sound of a lightning strike nearby, it sounds like a high-pitched crack. But if you're much farther away, you hear the very low rumble of the thunderstorm. The same sound was produced in either case. If you're close to it, you hear the entire range of frequencies, because the high-frequency sounds, that high crack, have not been forced to travel as far and have not lost as much energy when you're nearby. But when you're further away, all you hear is the low rumble, because those are those long wavelength waves which have traveled farther because they haven't lost their energy over this much longer distance. Second example is anytime there's a band playing, marching band or otherwise, if you are nearby, you can hear all of the parts of the band, but if you're far away, like say a couple hundred yards away, you might only hear the low thud of the bass drum. Finally, if you are upstairs in your room, let's say in your house, and your parents are talking to each other at normal volume down in the basement, there's one of them that you are far more likely to hear than the other, and it's your dad. And it's your dad because they tend to have deeper voices, and so those long wavelength, low frequency waves that they produce, sound waves, travel farther through the house, through the air, through walls, and whatever, than the, on average, higher frequency, shorter wavelength waves that are produced when adult women speak. And small children, like mine, can't be heard at all through the house. Another wave behavior that we talked briefly about with water waves is scattering. Scattering occurs when objects that are similar to or larger in width than a wavelength scatter waves. Part of the wave's energy is reflected back in the direction it came from, and the wave doesn't pass through the object without interruption. So, the big application of this to sound is with animals that use echolocation. So here's our example. Bats, for example, although there are many others, use echolocation to find their food. I like to give two examples of bats, one of which will starve to death and the other one that will be well fed. The hungry bat is the one that speaks in very low tones. If you are ever out in the woods at night and there are bats out looking for food, you will not hear them say, "Hey, I'm hungry, give me some food." You will probably, if anything, hear very high-pitched clicks or squeaks. And the reason for that is because of scattering. Here's my picture example. It'll look a lot like what you saw with a kiddie pool wave versus an ocean wave. Here is the bass bat's sound waves. The bass bat speaks in these low tones, sends sound out in low frequency sounds toward its food. This food, this fly or whatever it is here, cannot be resolved by the bat. It doesn't scatter the waves that impact it, that hit it, because the wavelength of this sound is too big. Scattering occurs here when the size of the object that's trying to be resolved is bigger than, the width of it is bigger than the wavelength. So here's a wavelength, and the width of this object is larger than the wavelength. So this fly ends up being seen and probably eaten by that bat because its wavelength is less than the object's width. And when we say that the wave is scattered, what we mean is a couple things. One, some of that wave energy is reflected back off of the object. That's how the bat uses it to echolocate. It's waiting for this reflection off of the creature. And the scattering of the wave is occurring here. It's that the wave is separated into two fronts, and basically that this zone right behind the fly does not have wave energy right behind it. The waves don't just pass through uninterrupted like they did over there. Finally, we talk a little bit more about bats and use the fact that high-frequency waves are scattered by small objects to figure out the size of the objects that bats are eating. So it is known, and you can Google search it yourself, but bats use frequencies from 20 to 200,000 hertz to echolocate. Sorry, not 20. 20,000 to 200,000. 20 to 200 kilohertz. The range of object widths that bats can resolve by those frequencies depends on the speed of the waves, which is the speed of sound in air, and their frequencies. And so we can find, using our wave equation, this range of wavelengths or object widths that bats are hunting for when they're looking for food. And so I've drawn them here to scale. Here is my finger, and it seems about right to me that the largest food that a bat might want to try to catch would be this big, and that the smallest would be that small. And anything bigger than this is not resolvable by bats, or at least they're not using echolocation to try to find those things. And anything smaller than that would be like this. It would not be resolvable, and it wouldn't scatter their sound waves.